Hello everyone, welcome to the review session. And today we are going to walk you through the important concept of computer architecture that we taught before the midterm. And hopefully that will prepare you better for the midterm. As we said, modern computer architectures are based on the so-called von Neumann architecture in a way that the computer is centralized by two important components, the processor and the memory. And in this picture, we also include the storage because right now it's hard to imagine that you have a computer or any kind of computer system without persistent storage, because we do want our stuff to keep persistently without fearing the loss of power or electricity during the execution, and also because we need the capacity that the storage device can provide. So, but set it aside. Typically, the common process right now when we want to execute a program is pretty much you launch a program that already exists in the storage or generated by your language runtime. And by launch, it means that you load the instructions and the data that are already encoded in a binary format that your processor can understand and accept into the memory. And when a processor needs to execute a program, the register that represent the current location of instructions will direct the processor to the right memory address to fetch the instruction that we want to execute. And the processor will have to look into the content of this instruction, and depending on what's inside that instruction, to know what are the corresponding operations that the processor needs to perform. And if the instruction wants us to access data, then the processor would additionally trigger a data access then. When the processor is done with an instruction, by default, the processor would go to the next instruction in a program order. However, in case there are some branch instructions, then the processor might go to different location than the next one. However, the importance of this von Neumann architecture and why it is so influential is because the good thing about this architecture is that by loading different programs into the memory, your computer can perform completely different functions without physically reconfigure the hardware. And the von Neumann architecture actually tells us how we can evaluate the program performance when we run it on the processor. So execution time is the performance metrics that most of the time we care about. And typically shorter execution time means better performance. And the most commonly measured unit is by seconds. And think about this. Because the von Neumann architecture executes instructions by instruction, and by default it goes to next instruction. So you can imagine your performance must have a big factor affected by the number of instructions that you are going to execute. And also, because your processor is controlled by clock, means that it only moves forward progress based on the advancement of a clock cycle. So what happened is that you can imagine since the processor executes instructions by instruction, so how many instruction instances that a program would incur, and how many cycles that it takes to execute an instruction, and how much time it takes for a cycle would actually determine the execution time. And that gives us the performance equation we want, which consists of instructions per program, or say instruction count, IC, cycles per instruction, or say CPI, or the seconds per cycle, or say cycle time. So, and the seconds per cycle, or say the cycle time, is typically the flip of your frequency. And right now, most of the processor runs at gigahertz, and you can easily convert 1 gigahertz as 1 nanosecond in this equation. So with that, it's if we want to evaluate the runtime of a CPU program, again, it depends on how many instructions it needs and how many instructions in each type, and how many cycles per instruction for each different types of instruction, and the cycle time of your processor would be the factor that you need to consider. So for this example, since we have 5 billion instructions, and each of this would, and 20% of them are instructions that takes 4 cycles, 20% of them are instructions takes 3 cycles, and the rest of them would take 1 cycle. So if the processor runs at 4 gigahertz, you can easily count the execution time in this way by putting 5 billion as the instruction count. And you can get an average CPI, which is 20% times 4, since 20% of the instruction would take 4 cycles, and 20% of the instruction would take 3 cycles, and 60% would take 1 cycle to get an average CPI, and times the cycle time. And that would give you the execution time for this case. And through the previous example, we know 3 main things are controlling your performance, namely the instruction count, the CPI, and the cycle time. And but what would affect those? So actually, as a programmer, you can control everything. And one of the obvious example is that by change the implementation of your program, you can change the CPI and the instruction count. So like this code example, the programmer actually add a sort before the main for loop. And without the sort, we found that the execution time is longer. So apparently adding the sort would increase the instruction count. However, we know the total execution time becomes shorter. So the programmer actually, by adding the sort, it make positive impact on the CPI. And so that's why for this particular question, we see the effectiveness of programmer in by adding a sort to make the CPI better. And this is another example how programmer can affect the CPI. So on the left-hand side, the programmer traverse I and then J. And on the right-hand side, the programmer traverse J and I. And as you can see, the instruction count is about the same. And because if you run it on the same processor, we can imagine the cycle time, the clock rate would roughly be the same too. So, but through our demo, you probably remember the left-hand side has better performance and the right-hand side has worse performance. So apparently, through the programmer's loop renesting, you see the better CPI on the left-hand side. And also, from our documents and some of the experiments you have done in a class, you know the programmer can also control the cycle time. So programmer actually has quite a lot freedom in control the performance. And programmer also can decide what kind of programming language that we want to use. And if we consider implementing Hello World, and Java actually has the most amount of instructions. And if you consider the amount of instruction that C programming language has to spin, there's no way Java can outperform C because of the intensive amount of instruction count it would incur. And the reason is because depending on how you implement your programming language, it will generate different instruction count. So for example, for a compile-based program, the generation of your binary is only a one-time cost. So every time when you run a program, you just need to load the compiled instruction directly into your processor. And because C programming language does not really have the concept of object-oriented design, so its code is actually the most compact and even compact than C++. And for programming language like Java, because we have to generate a code into the Java bytecode. It sounds like it's a good idea since it's also a compiled language. However, the Java bytecode is not the one that directly maps to your machine. And turns out every time when you run a Java bytecode, you need a runtime translation in your system to translate the Java bytecode into a binary code that your processor can support. And therefore, Java has the most instruction count among all the programming languages. And that's even worse than Python, because for Python, although we do need an interpreter, however, this interpreter actually directly generates the binary that you need for the processor that can directly execute without the need of without the very complex translation between bytecode and the binary. So that's why even Python is faster than Java. So some of you might be curious about how about compiler optimizations. So the thing is that a lot of you might think, why can't compiler modify the right-hand side as the left-hand side? And the answer is because the compiler can not really judge if a compiler optimization would affect the result of not or not. So even though I turn on the compiler optimization flag as -03, then your code on the right-hand side won't be able to become left-hand side because the compiler has no way to tell if the right-hand side, translating the right-hand side to the left-hand side would cause the program to fail. So also, if you think about the compiler cannot project what you really want at the end. So and compiler has no idea if adding some code would affect the correct result. So for the optimization that we performed in the past, like sorting the data before executing a loop, the compiler cannot do it. So that's why if you summarize all optimizations that in different levels, you will figure out programmer is the only one that can control both instruction, all of the factors, including instruction count, CPI, and cycle time. And instruction set architecture can only affect the instruction count and potentially the CPI when you are implementing your processor microarchitecture. And the compiler can control instruction count and the CPI, however, at a very limited scope. And the algorithm design definitely would affect the instruction count. However, that's also depending on how the programmer implements that. And programming language affects the instruction count and the CPI as well. However, a programmer can also control cycle time that others cannot. So I would say programmer is by far the most effective way of optimizing system application performance. So another way to judge if the performance is getting better or worse, we need to know the speed up of an optimization after applying an optimization. And in this computer architecture class, we have a unified definition of speed up in a way that if we want to talk about the relative performance between two machines, saying X and Y, and if we want to say Y is n times faster than X, then the definition is n equal to execution time of X over execution time Y. And or on the other way, you can say the speed up of Y over X would be execution time X over execution time Y. So if you use that definition, and if you consider a machine Y that we have here over the performance of machine X, you have to get the execution time of machine Y as well as the execution time of machine X and divide the execution time of machine X by execution time of machine Y. And then you will derive the answer 1.25 as the speed up in this example. And in this class, we also introduce Amdahl's law. And Amdahl's law is also an equation that tells us about the speed up. And it says the speed up as a function of f and s, where f is the fraction of time in the original program of a certain optimization, and the s is the speed up we can achieve of the f part of the program. So you might get confused here because I thought the execution time of the speed up should be defined by this. And the Amdahl's law seems to have a different format. And that's actually coherent with our universal definition of speed up in this class, because Amdahl's law is nothing but rescale the execution time as 1, as the baseline execution time as 1. So if you consider that, it's natural to see that if we have a part of a code that spent the amount of time as f, then the remaining part will be 1 minus f. And if we are able to enhance the f part with a factor of s, the new execution time of this f part will become f over s. And the remaining part will remain unchanged, and turns out it's still 1 minus f. So if you consider that, and you will figure out the execution time of the baseline is 1, and the execution time of enhanced would be 1 minus f plus f over s. So that's very coherent to M-DOS law. And so effectively, M-DOS law is nothing but a different format how we present the speed up. However, why we want to talk about M-DOS law instead of, in addition to the original speed up definition? Because M-DOS law provide a format for us to easily observe several insights. So first of all, we can definitely apply M-DOS law to multiple optimizations. And you can figure out that this optimizations, the synthetic effect of using all of the optimization together by applying M-DOS law by partition your program execution time into several different joint parts. And with that, we can have some practice of the M-DOS law. So for example, this is a very simple M-DOS law application where we found that 95% of the time can be optimized by replacing the hard disk drive with the SSD. So you can actually apply 95% and 100 into this M-DOS law equation and derive 17 times speed up. And if we have multiple parts of the and if you have multiple parts of the optimization, for example, we not only introduce the hardest the replacement of hard disk drive, but also a new processor. Then use M-DOS law, you can find the synthetic result would give you 29 times speed up. And the M-DOS law actually give us a lot of insights regarding performance optimization. So for example, the first thing that we can learn from M-DOS law is that if you want to find the maximum speed up of a certain optimization, you can assume the maximum speed up is infinity by in the M-DOS law equation. And then you can figure out if I work really hard into a certain part, it will give me the maximum available speed up of 1 over 1 minus f. And so that actually gives you an idea what's the maximum possible speed up of a certain optimization. So for example, if I want to spend time on optimizing a 16% part of the program, then it will at most give you 1.2 times speed up as we calculated. And it's almost impossible to work on the 16% of the time but still get twice speed up. And that's the first implication we will get. And if you use the first implication on multiple optimization, then you can figure out if I can only do one thing, and if I want to get a maximum speed up by picking one thing to do, then you should definitely pick the largest f as your target. And so the second corollary that we should get from M-DOS law is that when we are doing performance optimization, we should think about how to make the common case fast. And if you pick a very small f, it means that the optimization will have very little effect. And also, based on this corollary, you know the most common case here, it actually means the most time consuming. And it may not be the most frequently called function. It may not be the function has the most instruction count. It's totally by the most time consuming part of your program. And if you work on things that are not common, then as you can see from the previous example, it would only give you a very limited performance gain. And another thing that you should also learn from this is, if we look at, if we keep optimizing the most common part, then the most common part could change. So in one of our most early class example, that we already seen that the baseline program that sorts based on CPU and store data on hard disk drive, with the CPU, sorting would probably be the most time consuming part. And if if you replace the sorting and make it with a GPU version, then the sorting is becoming least significant than the I/O. But again, if you replace the I/O with a faster device, then the sorting or even something else will become the most significant part of your program. So optimization actually has a moving target as we continuously revise our program based on Amdahl's law. So another implication of Amdahl's law is that we should actually revisit Amdahl's law every time after we apply some performance optimization. And Amdahl's law can also tell us how good our optimization could be if we have multi-core architectures. So if we assume that we have a multi-core processor that is symmetric, what does that mean by symmetric? It means that every processor would run at the same speed and they would have the same latency to the memory subsystem. Then if we have unprocessor cores, and you can imagine the speed up would the maximum speed up that you can get from parallelizing your code would be 1 minus f parallelizable part of your program. And again, this f parallelizable means the time that in your original program that can be parallelized, and plus the f parallelizable part divided by n. So that's the law, Amdahl's law application to multi-core architectures. So with that, we can actually find out several interesting things. So first of all, if we assume that we have unlimited parallelism, and similar to what we have done to get a maximum speed up among optimizations is by replacing the number of processors with infinity, then you will see it's eventually going to be 1 over 1 minus f parallelizable. And that tells us a lot of things. So a few things that is interesting. Single core performance still matters in some sense, because if we are able to parallelize the program perfectly, and everything would eventually fall back to the single thread performance. And the second thing is that if we want to get our performance improvement more significant, then finding more parallelizable part is actually a key instead of and especially during the modern days that we cannot make single core performance even faster. And also, the hardware architecture should also focus on building a processor with unlimited parallelism. And the beauty of having unlimited parallelism is that even though the complexity of each single thread is higher, however, if you can make your program highly parallelizable, then your performance would eventually be better if your parallelism is rich. However, the parallelism is actually not text-free. So there might be a lot of synchronization overhead. And also, before you want to distribute the data, you actually have to prepare the data. And also, you might incur additional function calls if your threads are kind of like fine-grained. And there might be data exchange that you need between your parallel threads. So it turns out it may not be text-free. And in fact, most of the time, you would have you will have some kind of overhead added into your enhanced version. So it turns out the original Amdahl's law won't be applied directly. And you have to add, like this example, we have a performance rescaling function R here to evaluate the overhead of running program in parallel. And the thing is that if this overhead is too significant, which means that we are hurting the non-common part, the less time-consuming part, then it would actually burn out our performance gain. So for example, if my application of an optimization actually make an overhead that is 9 times longer than the original execution time of the remaining part, then although the original part only takes 10%, however, slowing this down would actually make the program even 10% slower than the past. So in summary, when we talk about speed up in computer architecture, there's only definition that is execution time x over execution time y. And M-loss law is another representation of that. And using this representation, we can actually get 6 different corollaries of that. First, each optimization has an upper bound, and that upper bound is defined by 1 over 1 minus f. And the second thing is, when we try to optimize our program, we should find out what the optimization with the maximum upper bound. And turns out that's the optimization with the most time consuming in the original program. And that most time consuming part is a moving target every time after you apply some kind of optimization. And if we apply M-loss law to multi-core architecture, then we will figure out that in modern architecture, exploring more parallelism is actually very important. And however, if we have unlimited parallelism, single core performance still matters. And also, when you apply the optimization, it shouldn't hurt your non-common case too much. So that's the implication that we will get. And when we want to compare our performance, it's also important that you want to make fair comparisons and choose the right metrics. And one of the potential things that we typically would fall into is that we take a partial metrics that only represent the performance of a partial part of your program instead of the whole program to represent the performance. And one of the things that easily lead to that consequences is using T-flops, or say flops, floating point operations per second, as a metrics. So floating point operations per second is essentially measuring the throughput of performing floating point instructions within a program. And if you think about how many floating point operations is actually derived from the instruction count times the percentage of floating point operations. And the execution time is also containing a factor of instruction count. So in this T-flops calculation, there is actually no consideration of the instruction count. So everything that would affect the instruction count is not in the picture of flops. So it turns out, if you have more compiler optimizations, if you have different instruction set architecture, then this T-flops cannot reflect that difference. And also, it's not representative if the application itself is not a floating point intensive one. So choose the right metrics. Choose the right metrics is really, really important. And most of the time, when we talk about the execution time, it means the end-to-end latency. And there are also other latency, like the disk access time or the UI response time, that we care about. And another one that usually hurt is the throughput. Hurt us to get the right insight is the throughput. So for example, the bandwidth, the number of operations that we can perform, or the flops that we have. So why latency and bandwidth may not be serve your purpose? Let's run through this example. So if you want to have a big bandwidth of transferring video, in fact, you can actually use a car to transport your data. However, you can imagine during the time that you are driving the car, there's no way your video can start. However, so the latency is actually worse than video streaming. However, if you consider that you can get petabytes of data within a short period of time, then it's actually a very good idea in terms of driving data using a car. So, but as you can imagine, the user experience is completely different. So it doesn't make sense for us to use bandwidth as a measurement for many cases, as you can imagine. Finished talking about the performance evaluation. Let's talk about the most, and from M-loss law, we know that we should focus on the most significant part of the performance problem. And apparently, in volume architecture, without any optimization, memory would be the most significant part of the performance bottleneck. And the reason why is because if you look at the evolution of performance in terms of processor and memory, with the advancement of MDOS law, processor speed can finish an operation within nanoseconds. However, for memory, it grows relatively slow, and turns out that we have a huge performance gap between performance processor and memory. So if you don't do any optimization in memory, there is no way the performance improvement in processor can help us getting better performance. And if you look at the evolution of performance in memory, it's actually not evolving a lot. So even though 16 years has passed, the performance that we get from the memory technology in 2000 and 2016 is still less than 2 times speed up. So and with that, if you consider the case we have in a previous figure where we access the access time of the DDR4 is without precharge is 26 nanosecond, and if you consider that and consider the fact that both instruction and data access needs to access memory, and without any optimization, even though each instruction takes just as short as 1 cycle to perform the computation part, the data fetch and data instruction fetch part would actually brings up the total CPI to almost 69 cycles. And if you think about that, 69 cycles, then it means that majority and actually more than 98% of the time we are spent in a memory. So because of that, memory is indeed the most significant part of executing a program. And there are indeed better technology that can replace DRAM. However, because of the cost, it's almost impossible for us to adopt them widely. So turns out the solution we have is to build memory hierarchy. And the idea of memory hierarchy is instead of you only use DRAM and processor, we also add a set of small SRAM serve as the cache of your data. And if we are allowed to use this cache to get 90% of the data, and as you can see from the calculation we have, because 90% of the data or instruction access do not need to go to the lower level memory hierarchy. So it turns out it only takes 8 cycles in total to get the data we want. And right now, we not only have one level of the cache, but also multiple levels of cache. Because if you do the math continuously, you will figure out as long as your data do not go to the DRAM, even though the lower level memory hierarchy is lower with lower accuracy, lower hit rate, we are still going to get a significant performance gain. So it's always a good deal to add more memory hierarchy if appropriate. However, here you might have a question why the idea of adding small SRAMs would help us to get better performance. And the magic behind that is because locality is everywhere in our program. So if we look at the code, which is the matrix vector multiplication code as I show in the left-hand side, if you consider the fact, then you will figure out that there is indeed spatial locality in which means that we tend to access neighboring items each time. So that kind of locality would help us to easily predict the item next to the current one is something that we would like to access in the near future. And also, we do have the tendency that we may revisit the same element again and again. So for example, the vector in this pieces of a code would actually get accessed many times in this pieces of a code. So that's the data access pattern of our code. And not only the data has locality, your code also has locality. So if you look at the right-hand side, which represent the real x86 code implementation of the loop on the left-hand side, you will figure that out. when we execute those instructions, we will keep going to the next instruction as this is the von Neumann architecture by default. So it turns out neighboring instructions are likely to be accessed in the near future. So that's actually spatial locality. And if you have a loop structure in your code, then you would access the same group of code again and again. So that also demonstrates temporal locality. So as you can imagine, in our code, or say our program in general, no matter it's the instruction part or the data part, they all have locality. And these two types of locality is called spatial locality and temporal locality. So because we have this locality, the strongest implication of that is that most of the time, our program is just visiting a very small amount of data instructions within a given window. So based on this policy, this idea, this insight, this is how we architect our cache. So first of all, if you consider the conventional access, we only access a word. And if your cache only cache a word, then it won't help you to capture the spatial locality. So to capture the spatial locality, what the best practice of your cache is that whenever we are accessing a word within your cache, we should fetch a block of data inside your cache instead of just a word that you are accessing inside the cache. So in this way, you are able to exploit spatial locality of your code. And so even though the next word is not driven by the previous access, we can still have it in a cache because we load a block of data every time when there is a miss occurred. And also, if we consider we have the spatial locality, and also we have multiple blocks typically we need to access, multiple data structure that you need to access, and it's natural that your cache needs to have the ability of accommodating multiple blocks. However, if we need to accommodate multiple blocks, an obvious question that we need to answer is that how can we tell which one is which? So that turns out that your cache architecture needs to have a field called tag that is allowing us to identify which block is within the cache. And also, you need to have valid bit and to tell if the block can be used or not. And also the dirty bit to tell you if the block is the only one that exclusively has the most up-to-date data. And within a block, because because block stores consecutive data, so we can easily use the common prefix of the data address with data or instruction address within a block as the tag part. So using the tag as the identifier of each block. And what happened when we access the cache is that, first of all, when we try to access the cache, we separate the offset part of the block. And then we compare the tag to see if anyone is a match within the cache. So this cache would work in a way that, okay, if I found it's a hit, then I can return the word immediately. And if I search out the whole cache array, but I don't find the data, then I will know it's a not found, or say it's a miss. However, the biggest problem is that to search the whole cache is an older algorithm. So if your cache grows larger, then your performance in searching the cache array, which needs to occur every time when we access the cache, will be a lot longer. So what we have to do is that we have to organize the cache as a hash structure. So an easy idea to make a hash structure is that we just directly map each block to a certain location within a cache. So this concept is called set. So what does that mean is that we can, for example, like this cache, we have 16 blocks within the cache. We can consider each block as a set. So what you have to do is that I just find a few bits within the address as the index that can help me identify if the block is within the cache, where is it in the cache? So if I use a bit 4 bits of address, which is good enough for me to address 16 sets within the cache as the index. So what an obvious thing to do is that for this particular address, I just need to go to the zeros index of the cache. And by just checking this entry, I know if it's a hit or not. And for the case that we don't find our content, you can also go to the number 4 set within the cache. And by comparing the tag there, you know the data that I'm looking for is not there. So this structure will allow us to always get the cache access time constant. And in a worst case scenario, it's still the same as the scenario that's not found. That's a hit. So it turns out that would actually give us the performance advantage. However, as you can imagine, as any of the hash table idea is that this kind of design would actually create a lot of collision problem. So a remedy of this is that instead of having one block within a set, we make our data way associativity. So way associative. So what does that mean by way associativity is that we allow each set to have multiple blocks to accommodate the collision problem. So what would happen in accessing way associativity cache is that we partition an address into block offset, set index, and tag. And we use the block offset to identify the right location of the word within a block, and use the set index to find out the potential set that the potential blocks that the right set that with the potential blocks that may contain your data. And if the tag, any of the tag within the set matches the tag of the searching address, we know there is a block within the set fits our demand. So this access will be a hit, and we just return the word from that hitting block. So as you can imagine, if I want to emulate the process of accessing the cache, it's very important for me to know how to partition my address. And we have a very quick formula to help us calculate that. That's actually C equal to ABS. And here, the C means the capacity of your data arrays. And the A means the weight associativity of your cache. And typically, if we say n-way cache, it means that n blocks within a set. So A would be set to that n. And if you have a direct map cache, like the earliest example, it actually means that you only have one block for each set. So the A is equal to 1. And the block size would actually means how many bytes of data can you accommodate within a block. And in a lot of places, we use a different terminology called cache line to represent the block size. And finally, a number that is typically unknown is called the number of sets. And if it's a fully associativity cache, then the number of sets is simply only 1, because it means that your cache can go anywhere in a cache. It means that your data block can go anywhere in the cache. So using C equal to ABS, and by having all of the values of C and ABS available, you are able to get the number of bits in block offset using log B. And you are able to get the number of bits in set index using log S. And the remaining bits in your address, that would be the address length minus log S minus log B. So if you have a 64-bit address, and that would become 64 minus log S minus log B. So saying that I have an NVIDIA Tegra processor, how do I know how to partition the address? And the answer is also easy. We can just apply C equal to ABS, and then we will figure out the S is 128, which means that the offset in your address would be 6 bits, and the index in your address will be 7 bits, and the tag will be 51 bits. And for Intel Core i7, which is identical to the cache design of the core design of what we have on the data hub, is a 48 kilobyte, 12-way, 64-byte block designed cache. So in that case, we still use C equal to ABS, and we can know the S is 64, and the offset will be 6 bits, and the number of bits in the index will also be 6 bits. So it turns out the tag will be remain 52 bits. And that's how you partition the address in Core i7 processor, or in general the Core i3 processor that we use in the class. And let's put everything together. This is how cache interact with the GPU. So saying that, right now, if I send a request to the cache, and again, in memory hierarchy, we call this hierarchy because your processor is only allowed to interact with the L1 cache directly. And if you have a load request, and again, you will have to partition the address into tag, index, and offset. And you through the process that we described before, we will know if it's a hit or a miss. And if it's a hit, then we just directly return the content. And if it's a miss, we have to accommodate the block that we need to read inside the cache, because again, the processor only interact with the L1 cache. And if you're lucky that the cache is currently not full, you can get a block inside the designated set directly. However, if the set that your block will go is full, then you have to find a victim block, which means a block that you need to kick out from the set. And if you are fortunate enough that the victim block is a read-only block, then you can directly kick that block out. However, if it's a block that has been modified, then it means that if you directly discard that block, then no one else in the system will have the up-to-date correct data to operate. So it turns out you have to write that content back to the next level memory hierarchy. However, and then after you write back, you can finally issue the fetch block command to the next level. However, sometimes you may not be that lucky. The block that you want to fetch may not also exist in the L2 cache. So it turns out it will trigger another mishandling, which might require you to write back a victim block in the L2 cache before you can fetch the demanding block. So once you handle those misses, you can finally fetch the block and return the block to the upper level memory hierarchy. And that's when we want to read the data. And if you want to write the data, the process is similar. However, the difference is that when you have a miss, you have to set the block to dirty. Otherwise, in the future, nobody would know this block has been modified or not. And then, similarly, if it's a write miss, again, because your processor only interacts with the L1 cache, so you have to fetch the block into the L1 cache for your update before you can perform the operation. And if your target set is full, then again, you might have to kick out a block first. And if the block is unfortunately being modified before, then we have to write back. And similar to what we just described, if all the victim blocks are dirty, you have to write them back before you can fetch them. And then return the target block and perform the update in the L1 cache. And based on that, you are actually allowed to evaluate the CPI of the cache by knowing the performance, by knowing the process of that. So for example, if I have an application with 20% of the load store instruction, and if I have a cache miss rate of 5% for the instruction cache access, 10% for the data cache access. However, for the data cache, there might be 20% of the data that is dirty, and for L2 cache, the miss rate is 20%, hit time is 10 cycles, and 10% of data that is dirty, and the main memory may have a 100 cycle latency. I can calculate the CPI by walk through the process of accessing cache as below. So first of all, through access the instruction cache, I know, and 95% of the time, your data will have no additional overhead. And however, 5% of the time, it would be a miss, which means that you have to fetch a new fetch a block from the L2 before you can perform instruction access in L1. So it turns out you need to incur an additional L2 access, and then if the L2 access is still a miss, then you have to access the lower level memory hierarchy. And if the data that you are going to replace in the L2 is a dirty block, it means that 10% of the chances you are going to incur one more access to the lower level memory hierarchy. So, and that additional access would also cost 100 cycles, and before you can return the instruction. So it turns out, if you walk through that process, for each instruction, the base CPI is 1 cycle, means that it only takes 1 cycle to execute the instruction itself without memory access. However, 100% of the time, you will need an instruction memory access because that's the instruction itself. And 5% of the time, which is the purple part, you will get a miss, which will incur 10% of the 10 cycles of the overhead at least. However, 20% out of this 5%, you will have to access the DRAM. And when you access the DRAM, 10% of the time, you are going to write dirty data back. So it turns out you are going to incur another 100 cycle overhead. And when you access the data, it follows a similar path in a way that if you have 10% of the data that is a miss in L1 and 20% of them could potentially be dirty, that means that 20% of the time, each L1 miss would incur 2 access to the L2. So turns out the calculation would be 20% of the load store instruction will have 10% of them would at least require 10 cycles. And however, it's not only this 10% because 20% of this 10% will have to have an additional access to the L2. And when you access L2, it's not just 10%, it's not just the 10 cycle, but also 20% of the time you will have to access the DRAM. And again, when you try to get data into the L2, there might also be a chance that you are going to get dirty blocks. So on average, the CPI would be 3.4 in this case. All right, so figure out the performance of having in-memory hierarchy. It's also important for us to figure out how to improve the performance of memory accesses. And if we want to improve the memory access, improving the miss rate is actually a very important thing to know. And to know how to improve the memory performance, or say the cache miss rate, we actually need to know the cause of cache misses. So in general, we can categorize all the cache misses into 3 different categories: compulsory misses, capacity miss, and conflict misses. So compulsory miss means cold start miss. So whenever you first time access to a cache block within your code, within your program, that's called compulsory miss. And capacity means that the memory footprint of the current application, or say with the period of time, is just within a period of time, it's just bigger than the cache size. And without increasing the capacity, there's no way we can avoid that kind of miss. And conflict miss means the required data was once in the cache before. However, it's no longer in the cache because we have a conflict in the weight associativity in the same set. So that's similar to the collision problem in a hash. And that's typically because the weight associativity limits the amount of blocks that we can accommodate. So in other words, if it's a miss that by increasing the associativity, we can alleviate without affecting other factors, then it means that's a conflict miss. So we can simulate the cache with the concept of causes of misses and with the concept of how to partition the address in play. And here's the tip. So first of all, if I want to simulate the cache behavior for a pieces of code, I have to figure out what are the memory access patterns. And I would generate a sequence of addresses that my code would access. And then I would try to figure out for this pieces of code, is there any kind of locality or variables that would help me to generate the insights? And Then with the generated address sequence, I can partition the address and figure out the tag index to know how to search the cache. And then you probably also need to bookkeeping what's currently in your cache content in a way, what are the tags and the index of the content in your cache. So if you find the same index and the same tag that remains in your cache, that means that it's a hit. Otherwise, it's a miss. And for the miss, you always have to figure out if it's a compulsory miss, conflict miss, or capacity miss. And if there is a miss, you also need to replace the least recently used block within the requesting set. And so let me walk through a very simple example for simulating a direct map cache. So if you are given the following memory addresses, and if you have a direct map cache with 256 bytes capacity in total, block size of 16 bytes, you C equal to ABS, you are able to know that there are 4 bits in the index, 4 bits in the block offset. So for each of the address, you can partition them with 4 bits of the index, and the remaining bits are the tags. And then for accessing the first one, because this is definitely the first time I see the block, so it will be a compulsory miss. And to serve this compulsory miss, I will have to fetch the block inside this direct map cache at the designated set, which is set number 1 here. And then once you are done with that, the next access, which also point to the same tag, the same index, would be a hit because that's currently in a cache. And the third address, as we can see here, is going to a different index, even though the tag is the same. And because this is the first time we see this combination in our program execution, so it's definitely considered as a compulsory miss. And to serve this compulsory miss, again, we are going to put this block inside the designated set of the cache. And then for the fourth address in this example, because it goes to the same index and we do see the same tag, so it's going to be a hit. And for the fifth access, although it also goes to set index number 1, however, because the tag is different, and this is also the first time we see this combination of the tag and the index, so it's going to be a compulsory miss. And when we serve this compulsory miss, because this is the direct map cache, so we have to kick out the current block inside the set with a new block with the desiring block. And now, when we go to the 6th address, it also looks for index 0, and it's still the block that we want. And same thing for the next one. However, when we go to the second last one, it goes to index number 1. However, because that block has been there before. However, when we serve the compulsory miss of tag 11, it's actually kicked out. So that's actually a conflict miss. So it turns out to serve this conflict miss, we again fetch this block back so that the next one will be a hit. Use a similar approach, we can also simulate a two-way cache, and we can know the division of the address, that 3 bits of them will be in the index, 4 bits of them will be in the block offset. And for the two-way cache, it means that the same set would contain 2 different blocks. So for the first and all the address, we can partition them accordingly. And because there is only 3 bits in the index, so you will see the tag has 1 more bits now. So the first access is still a compulsory miss, and it will be placed in index 0. And for the second access, it's the same block that we just fetched, so it's still a hit. And for the third address, it's going to be in index 1, and because we don't have it before, so it's a compulsory miss. And the follow-up would also be a hit. Now, when we serve the 5th request, it's going to index 1, and again, it's a compulsory miss because that's the first time we see it. However, now, because we have two-way associativity, so it means that each set can accommodate 2 blocks, so there won't be any replacement happening here. And the next one, the next 2, they are all hit because set 0 still contains that block. And the last two, unlike the previous case, it will be a hit because in the previous one we served the compulsory miss of tag 110. We didn't kick out anyone. So the remaining one will all be hit when we have a two-way set associativity cache. We can also do this in real program with real processor. And through this example, we figure out that, okay, use equal to ABS, 7 bits in the index, 6 bits in the offset. And the same technique, we should list all the address, partition them. And through the process, you will figure out, of course, the first few blocks, they are always compulsory miss. And when we go to the fifth address access, which is the E0, and when we access this block, because this cache only have 4-way set associativity, so it can only accommodate up to 4 blocks within the set. So although this E is a compulsory miss, but when we serve this, it will actually kick out the block containing data A0 to A7. So now, the next time we want to serve A1, although it was a block that we have seen before, but because it was kicked out when we served the request for E0, so it turns out this is a conflict miss. And when we serve this conflict miss, we keep kicking out B. And so it turns out if you continuously do the math, repeat this process, you will figure out there's 100% miss rate. And only for the first access to the block, you will have compulsory miss. Other than that, everything is conflict miss. But if you can increase the weight associativity, like the Core i7, except for the first few blocks that we have compulsory misses, and because we have sufficient amount of weight associativity, so when we serve the E data structure, we don't need to kick anything out. So it turns out everything else will be a hit. So for this case, the hit rate is significantly better, and you're only going to see compulsory misses in your code. So in this way, you can see how effective in increasing weight associativity in improving the cache performance in terms of conflict misses. Sometimes we have problem. You may have trouble identifying the difference between conflict misses and capacity misses. So let me walk you through one of the example that you have in the homework. For this is the code that we have in the homework. So consider the case where size is 16K and the argument, or say the stride, is 16. And the first few, we have no trouble identifying it as compulsory miss. And we can fast forward our access to 512. And as you can see, that's still a compulsory miss because that's also the first time we access the block. And with that stride, every time when we access an element, it's going to be in a different block. So now, the last one, in the last one block that we are going to access in this data structure is actually 16368. And the first time when we access that block is also a compulsory miss. And then we will be wrapped around back to our beginning of the array. That's data 0. And for this one, because that's again the first time we access, that's no longer the first time we access this block. So that's actually not going to be compulsory miss. However, how can I tell when I access data 0 again, it's going to be a capacity miss or a conflict miss? It totally depends on how the amount of data that we have access between the first access to data 0 and the second access to data 0. So if you check the amount of blocks that we need to access, it's actually 1024 blocks that we need to access. And to store all the 1024 blocks, because each block has 64 bytes in space. So turns out you need a 48 kilobyte of cache to keep everything in there. So what does that mean? Is that even though you have very unlimited number of weight associativity, as long as your capacity is less than 64 kilobyte, then there's no way I can store I can keep data 0 remain in the cache. So this one, I would say this is a capacity miss. However, if we consider the case where the stride is set to 1024, and when I fast forward to the end, everything for their first time address is a compulsory miss. And when I wrap a run back, at this time, I have only accessed 16 blocks, which perfectly would fit into the cache. However, just because this cache doesn't have sufficient amount of way associativity to accommodate this 1 kilobyte of data, so even though my cache still has space, I will still have a miss here. So this one is going to be a conflict miss. So hopefully that would help you clarify what's the difference between conflict miss and capacity miss. And again, we care about performance. We want to know how to improve the performance. So, as we mentioned before, programmers are the most effective. So a few techniques that we have introduced in this class. For example, you can do loop interchange, loop fission, and loop fusion. So loop interchange means that we just alter the order of traversal using different traversal order of the index. And that would actually make our locality better. So that's one way. And loop fission is accommodating the case where we don't have sufficient amount of way associativity, and you try to reduce the number of different data structures that you want to access within a window of time. And for the Tegra processor, if you change your code from the left-hand side to the right-hand side, it will make better performance. However, if you have a processor with rich way associativity, you probably want to do loop fusion, like the changing the code from the left-hand side to the right-hand side in the loop fusion example. And so from our demo here, it's definitely a loop interchange example, so you can know the left-hand side is better. And for Tegra processor, using loop fission would actually bring down the cache miss rate from 100% to 10%. And if you have a processor like an Intel processor, the right-hand side would actually be better because the number of memory references is smaller, and both of them already have very high cache hit rate. And another optimization that is a common practice called tiling. So for example, matrix multiplication, by default we use a 3-level nested loop. And however, if you consider this 3-level nested loop, and if you have a 1K by 1K matrix, then each row itself already take 8 kilobytes. So if you have a 32 kilobyte of cache, it can only give you at most 4 rows and column in each matrix. So if you use the algorithm, the original algorithm, you can easily create capacity miss or conflict misses because you have limited way associativity and limited parallelism to accommodate all the rows and columns that you need. So the better way of handling this is actually using a tiling algorithm that restrict the amount of data that you need to access within a period of time by just calculating on a specific portion of the matrix that you want. And in this way, you can restrict the size of data that you need to access every time. And you can also, by considering the number of way associativity you have, you can also set a tile size to fit that. So it turns out that you can avoid both conflict misses and capacity misses by using tiling algorithm. And you can additionally apply matrix transpose to make sure that you can even exploit spatial locality when you perform the arithmetic computation. And that would actually help us to further remove the conflict misses. There are other mechanisms that can help us improve the performance. For example, we can apply the idea of prefetching to use the free bandwidth when we are accessing, when we are performing computation to fetch the data that we might need in the future. And the prefetch can be done in both software and hardware. And for the hardware approach, it typically requires the processor to have some kind of predictor that observe the behavior of your memory access pattern. And for software prefetch, the programmer can insert prefetch instructions. However, both software and hardware approach would require your code to have behavior that is easy to predict. However, is that often? So within this 4 code snippet, only the second one is predictable. So it's really important that the programmer understand that we want to make our code easier to predict for even software predictor, compiler optimization, or the hardware predictor. And another thing to worry about is that prefetching, because we make the memory access happen ahead of time. However, if your cache is not big enough, what would typically happen is that when you prefetch the block, the prefetched block will compete the same location with data that you might need to access sooner than the prefetched block. So it turns out it will hurt your cache performance. So the better idea is that instead of having the prefetched block placed inside the L1 cache immediately after you prefetch, you probably want to have a separate buffer so that it won't kick out the real stuff that you need in the cache. And also, similar to this idea, there are missed caches that also cache the missed content in a small buffer. So in case we have a conflict miss, you might still be able to find the kickout block within the missed cache. Or another idea is that we can more efficiently use the small buffer by using the concept of victim cache in a way that we use a victim cache to store the evicted block. And so that if we have if we are just short on one-way associativity, then we can easily find that evicted block within the victim cache. So that even for processors like the NVIDIA Tegra processor running our code example, you can still always find the kickout block in the victim cache. So those are the hardware optimization we have. So as a summary, the hardware optimization can actually help us to address the conflict miss and compulsory misses. And for software programmer, you can actually address everything through data layout. You can avoid capacity miss, conflict miss, and compulsory misses. And for blocking tiling, you can actually address the capacity miss, conflict miss. And for loop optimization, depending on what kind of cache you have, you might take a different strategy. So those are the optimizations that we have learned. And finally, we talk about virtual memory. So virtual memory is actually allowing us to run multiple processes at the same time, or running a program that is larger than your physical memory installed. So the concept is that we just redirect each process to run within its own virtual memory address space. And somewhere in your system is going to translate the virtual address into physical addresses. So for example, if I have two programs that I'm running, the virtual memory abstraction would create two abstractions, two separate address space. And dynamically, depending on what data we are loading or accessing, dynamically allocate a page inside your physical memory location so that both programs can enjoy a limited set of physical memory locations. However, if you need to access more data than your physical memory, then you can also use a similar concept as the caching idea we have by just kicking out the stuff that is currently in a physical location to a swap space that's typically on your persistent storage as an extension of your memory locations, so that the physical memory right now acts like a cache for virtual memory, and your persistent storage actually has the universal set of the data. So this approach is common practice called demand paging and swapping. But as we can see, a key key element that can drive this idea is that we can perform address translation between virtual address space and a physical location. And if you naively implement a 1-1 mapping table, it actually needs petabytes of data. So modern systems, we actually use a hierarchical page table that actually use perform address translation in a B-tree-like fashion to save space. However, the consequences is that each address translation would take multiple memory accesses. So, for example, if you have a data access instruction in x86, in a worst-case scenario, you may have to access memory for 10 times because we need 4 of them in translating the instruction address and 1 real instruction fetch, and also 4 of them in translating the data memory access address and 1 for the real data access. So the optimization that we would take is called translation look-aside buffer by adding a small translation adding a small cache that stores the translation between virtual address and physical address. Then every time when you access the data, you ask the TLB first before you access it. However, as you can imagine, the hit time becomes really long because you always have to consult the TLB. So an idea is to use virtual address in your cache. However, because the same virtual address may exist in multiple applications, so it won't work out. So the common practice right now is use virtually indexed and physically tagged cache. And the basic idea of virtually indexed and physically tagged cache is to ensure the set index and block offset resides within the page offset, which is the part that remains the same before and after translation. So turns out with that, one thing we can do is that, okay, when we partition the address, because the set index and block offset, they are within the page offset range. So they will be the same before and after translation. So it's safe for you to use the same set index to access the cache. And in the meantime, you can translate the virtual page number, use the TLB. And if and in your cache, you also store physical address as your tag. So it turns out when you access the cache, it's effectively as use physical address to access the cache. And when you use the virtual page number to search the TLB, you will output a physical page number, which can be used to compare with the tag, which is also from the physical address in your cache, to consider if this is a hit or miss. So that means that at the end, we are still using the physical address to compare if it's a hit or a miss. However, when we use the index, it's actually from the virtual address. So this actually perfectly resolved the issue of virtual cache. However, it also created another issue, is that because it requires your set index and block offset to be within the page offset. So always your log B plus log S in the C equal to ABS has to be equal to 12. So if you have one-way set associativity, or say a direct map cache, your capacity is only 4 kilobytes. And if you want to make it 32 kilobytes, you have to go to 8-way set associativity. So I hope this would give you a good idea about what's going on in the class before the midterm, and hopefully that will help you capture the important bits of this class. And enjoy the preparation of your midterm, and good luck on your midterm. Goodbye.